All right, so we're going to discuss today the property of feedback to help us do bandwidth extension. And if you remember, or if you recall that diagram that we have of the feedback with the beta network and the forward A gain, that A gain block normally refers to an amplifier. Okay, it doesn't have to be an op amp, but these days it could be an op amp more than likely if you're doing some type of board level analog design, or if you're doing a integrated analog circuit, then it's an amplifier like an op amp that is monolithic, that is integrated on a chip, and you are using that block. Now, this amplifiers in general have two characteristics that feedback helps us deal with. One is the high gain. So feedback, as we explained, help us tame that high gain. But another important characteristic that is typical of these amplifiers is that the amplifier tends to have a single high frequency pole. Okay? So that's just the nature of the construction of the circuit. So if we take a closer look at that 8-block transfer function in the Laplace domain, we can express that gain, which is frequency dependent. Notice the dependence on S, as some constant, which is the mid-band or mid-gain frequency. So this is the mid-band frequency, or gain, rather. Okay? And then it's going to be a single pole, so it's going to be a first-order system. And that can be expressed as omega h, which is that high frequency pole. Okay? So that is just the open loop gain. Now, if you expand that to the closed loop gain, then you would get a frequency dependent closed loop gain A sub f, which is the open loop gain, and that's just an application of our closed loop gain equation. Okay? And we can then expand that using the expression of the open loop gain from the previous screen, and we get this constant divided by this expression, omega h
Sorry, was the the first equation the open loop above that technically? Or wait, this one right here is the closed loop gain.
That's the closed loop gain.
Yeah, this is the closed loop. The one before that was
that was the open loop gain of just the A block.
Okay.
Okay. So that now we have an expression of the closed loop gain that comprehends that frequency dependent nature of the amplifier that we're trying to apply feedback to, and also our feedback, which is our beta network. Okay? So from there, if we compare that to the original expression, we see that with feedback, the midband gain is the open loop midband gain divided by this expression, which is very close to the amount of feedback. And from there, again, by comparison with the original expression and what omega H was, that high frequency pole, we see that the new, with feedback, the new high frequency pole is the open loop pole times 1 plus the open loop midband gain times beta, which is greater than 1. So we have essentially, for the closed loop system, extended the bandwidth. This implies that at the same time that we have done this, of course, like we showed last time, we have reduced the gain. So in amplifiers, there is this constant quantity, which is the gain bandwidth product. You can extend the bandwidth at the expense of reducing the gain. And that's okay, because normally we don't need the astronomical type of gains that these amplifiers have, but we do need extended bandwidth. So to close this part, I'd like to show a picture of the book, and I'll be doing this throughout the semester. I'll be using a lot of pictures from the book, so that's another reason why you need the book, so you can refer back to those, to the ones that I show. So I'm going to
Dr. Hernandez, what does WH stand for?
That's the high frequency pole. So that's omega that's the natural frequency of where the high frequency pole is. So omega H would be equal to 2 pi FH, and FH would be the frequency where the high frequency pole takes place. So if you look at the gain, the open loop gain, okay, as a function of frequency, you may see something like this. And this will decrease at 20 dB per decade. Okay? And here where you have that would be, and then that's omega H. So this is the high frequency pole that we are talking about. And you may have another zero pole down here, but it doesn't really matter at that point. Normally, this is the characteristic that we're talking about. Does that answer the question?
Yeah, it does. Thank you.
And then what happens is, if this becomes, what we're saying is that if this now becomes the closed loop gain, you will get a reduction in gain here, an extension on bandwidth, and this would be the the new closed loop bandwidth. So you get a reduction. So this slope here gives you that gain bandwidth product. So you can see your gain goes down and then the bandwidth gets extended. So you get this extension of bandwidth by this reduction in gain. Okay? So this is your open loop gain here. And this is your FH. So you can see that here, right? And then you reduce the gain, you extend the bandwidth, and all this has the quantities with the logarithms and all that, so much nicer than what I drew, but it's essentially showing the same thing. Okay. And then again, the omegas are just 2 pi this quantity. So omega h is 2 pi fh, and omega hf is 2 pi fhf for the closed loop case. Any questions about this this figure? All right, so since I have the book here, let's go to the next item, and let's talk about another benefit of feedback, which is the reduction in nonlinear distortion. So for that, a good way to look at that is to look at figure 11.6. And this curve A refers to the open loop nature of the amplifier. So you may have some linearity. So this is a V input. So this is the input to the amplifier versus the output. In real amplifiers, what is going to happen is that when the inputs are very small because of the high gain, you get some linear relationship. You get some linear relationship with the output. But then at some point it's going to saturate. At some point it's going to saturate. So because of the power supply. So that's the saturation for the open loop case. Okay, at the negative and positive power supplies. But if you reduce the gain via feedback, now you can present higher inputs or a higher dynamic range at the input, and still get a linear relationship. So you get an expanded input dynamic range that reduces the nonlinear distortion of the open loop case. Because this saturation is a nonlinear distortion. This is saying that you change your input, but your output doesn't change. That is a nonlinear behavior. Okay? So by expanding the dynamic range of the input, you reduce the nonlinear distortion. And you have seen this with op-amps without feedback. They're used as comparators. Why? Because it has this nonlinear behavior. A comparator is a nonlinear device, and you actually take advantage of that high gain. And also, specifically in op-amps, the characteristic of the virtual short of the inputs is because of that behavior. Because it's saying that if you want your op-amp to operate linearly, which is where you want it to operate, then the input difference has to be very small. So this axis here, that is the positive input minus the negative input. So that this is a differential voltage. So this is saying that if you want the op-amp to be in the linear region, which is where you want it, then the difference of V plus and V minus, the difference of those inputs needs to be very small. And what does that mean then? Well, that means that if the inputs are very close to each other and the difference is very small, that's what we call the virtual short of the inputs for the op-amp. That's what it comes from, that characteristic. So feedback allows us to increase that input dynamic range, which in turn is the same thing as reducing the nonlinear distortion. Okay? Start getting more specific about these amplifiers and talk about feedback voltage amplifiers, which you have used, but we're going to take this more disciplined look at their characteristics in the presence of feedback for this feedback voltage amplifiers. Okay? And we're going to see that there are several configurations depending on, we're going to extend this discussion to other configurations depending on how you're sampling the output, putting it through the beta network, and getting that feedback signal that you couple into the input. And we're going to see there are two ways of sampling and two ways of coupling, so we're going to end up with 4 different topologies. Okay? But the first one that we're going to look at is the series shunt feedback topology. And shunt refers to in parallel. Okay? Now, in this terminology, the first word refers to how you are coupling the feedback signal into the input of the amplifier. And remember that you're coupling it with the input of the overall system. So that's also called voltage. If you're doing series, the first word refers to the coupling, and if you're doing series, you're doing voltage mixing. Okay? The second word refers how you are sampling the output. And if you are doing parallel sampling, then you're doing voltage sampling. And you can see, as we'll see later, how you can have 4 different configurations. You can have all the combinations of voltage mixing or current mixing and voltage sampling or current sampling. Okay? So
can you just explain the coupling thing again?
So the coupling is if we go back to our, and I'll show some pictures later, but to go back to the diagram that we had discussed, we have the our input to the system, and here we had the feedback signal. This is our beta network, and here we had our error signal into our A and our output, So the mixing refers to this part. So we're coupling the feedback with the input of the system. So we're mixing VF and VS to generate VI, which is really an error signal that drives that amplifier. That is the mixing part. The sampling is on the other end. Here, we are sampling the output and inputting that quantity into the beta network to produce the feedback signal. So this is the sampling, and this is the mixing. Now, this is a general diagram. This is agnostic to whether we are doing current or voltage sampling or current or voltage mixing. This is really an agnostic diagram. We're going to see the specific topologies of the different ways of mixing and sampling when we look at this specific amplifier with feedback topologies. Did that answer the question?
Yes, thank you.
All right, great. So let's just stick with the voltage mixing and the voltage sampling, which is what you're most familiar with. So this is like your negative gain amplifier. Okay. So, and you're familiar, in this case, the beta network is just those two resistors. So, but from an analysis, more disciplined perspective, let's look at that topology. So let's do a bit of analysis here. And the first thing that we want to do is determine beta, okay, and our closed loop ideal gain, okay. And we can do that because remember that the ideal gain is just 1 over beta. And if we go back to the general system diagram, and we remember that beta is the transfer function of the feedback network, and we're talking about voltage sampling and voltage mixing for this specific topology, then that transfer function beta is going to be the voltage from the beta network. So that's the output of the beta network over the voltage into, so the input into the beta network. Okay? So what we can do with that is to determine the loop gain, which is so important, which is A times beta. And what you find is that the loop gain is, and this quantities VR and VT will be apparent in a second, using our technique of breaking the loop. So if you recall, we had this way of breaking the loop by setting the input to the closed loop system to 0. This is going this way. And here we have A going that way. And then we had broken the loop. And we know that this is the output here. But we have broken the loop here and called this node VR and this one VT. In a sense, we had said we break the loop and we put a test signal. That's where the T comes from. And we look at the VR signal, which is a response to the test. That's where the R comes from. And that gives us the, if you solve this diagram and you get a ratio of VR over VT, essentially output over input, and we know that that feedback is negative, that gives you the loop gain, which is a very important quantity. And then, actually this was 2 here. And then what we can do, so these are the types of analysis that you can do with these different topologies. And we'll look at all of them, but this is the most widely used, so that's why we're spending so much time with it. What we can do as well is find and compare the closed loop gain, which is the open loop gain divided by 1 plus the loop gain, and compare that, because that's what we care about, the closed loop gain, but we also want to know how close it is to the best case scenario, so we can compare to the ideal closed loop gain, which is 1 over beta. Okay? So let's see. I'm trying to find a way to optimize the back and forth of the book and my notes. So I'm kind of keeping in mind the pictures that I want to show and go back and do that, but without really getting too far away from the topic. So that'll be a balancing act. So I think it'll be okay to go and talk about the other types. So I said that this was coming. The other types of feedback So what are the other types of feedback amplifier? And remember that you are changing 2 characteristics, okay? The sensing and the mixing. And how you do those is what gives you the topologies. So we have looked at 1, there are other 3 topologies. So in essence, we can build a table. So we can say here sensing, mixing. What is the AF for that case? What is the amplifier type? And what is the mixing, sensing, feedback topology? Remember that the first word refers to the mixing. So we can construct as a table. So first, we can sense voltage and mix voltage. We saw that. In that case, the closed loop gain, you're familiar with this, is the voltage output divided by the voltage input. And that's simply a voltage amplifier. So we have series, shunt. So I'm going to use SE for series and SH for shunt on the sampling. We can sense current and mix voltage. So in that case, the closed loop gain would be an output current over an input voltage, and that is what we call a transconductance amplifier. Okay? Probably number 2 in the list of usefulness. So we do use transconductance amplifiers to generate current sources and things like that, and biasing networks. So in that case, the mixing, since we're still mixing voltage, that's still series. But then, since we're sampling current, the sampling is series as well. So that would be a series feedback topology. Then we can have sensing of current and mixing of current. So that would be a current output. The closed loop gain would be a current output divided by a current input, or S rather, and that's simply a current amplifier. So since we are mixing current, we do that with a shunt topology on the mixing side, and since we are sensing current, we do that with a series. So that will be a shunt series feedback topology. And finally, we can sense a voltage and mix a current. So in that case, our closed loop gain would be an output voltage divided by an input current. And that would be then a trans resistance amplifier, in which we have shunt mixing of the current and shunt sampling of the voltage. So the way that they are listed in this table is sort of the is based on popularity. So what you work with the most will be voltage amplifiers, and then transconductance, and then current, and last but not least, trans resistance amplifiers. But those are the four topologies. I'm going to show a series of pictures from the book now, but of interest in any amplifier, and we have been emphasizing the closed loop gain, but there are 3 main things that you want to know of any amplifier. As we go and discuss more amplifiers at the circuit level, we're going to see that we're going to pay more attention to all 3 of them. But here at a sort of a system level, we have been emphasizing on the closed loop gain. But at a circuit level, equally important are these 2 things: input impedance and output impedance, because you want to know how your circuit is going to load whatever is driving it. So that's the input impedance. And you want to know also how well your circuit can drive something else that comes after it. That's your output impedance that relates to that. So these are going to become like the main characteristics of amplifier-based circuits that we're going to be looking at. All right, so let me stop here and see if there are any questions at this point, or anything that you want me to go back to.
So mixing doesn't directly mean series, right?
No, mixing refers to the coupling of the output of the feedback network with the input of the system. But you can do mixing, shunt mixing, and you can do series mixing. Was that the question?
Yeah, that made sense. Thank you.
All right. All right, so then let me go back to the book and show some pictures.
Question, Professor?
Yeah.
For the analysis part 1, what did you have for the beta equals? I missed that.
For
analysis part 1, determine.
Oh, okay. So I had this expression here.
Yeah.
I concluded that part saying that the beta was the transfer function of the feedback network, and that was essentially the output of the beta network. So that's the voltage coming in the case. Remember, we were talking about voltage amplifiers and voltage mixing and voltage sampling. So the gain beta or transfer function of the beta network is the output of that beta network. So the voltage from the beta network divided by the voltage into, so the input to that beta network. And that's exactly what I wrote. The first thing that I wanted to show is better set of pictures for a practical series shunt feedback amplifier, which is the voltage amplifier. So you can see here where let's see here. So you can see here where we are sampling the voltage. Okay. Now this node here, you can think of it as ground. So you're really sampling the voltage here at this node. That goes into the feedback network. So we are doing parallel sampling or shunt sampling because we are in parallel with these two ports that are coming out of the basic amplifier. And here we are mixing in series. Here we have our source signal with some output impedance. So this is the source resistance of this source. So the output of the amplifier is right here. So we're mixing that in series. So here you can see that this node and this node are in series with what's going into the amplifier over here. Those two ports. Okay? And later on, things that affect our gain and the impedances of an amplifier where, this amplifier is inside, that is the basic amplifier, but really there are input impedances. There are input impedances which is the absorption of that at S, and also over here there could be an input impedance of the amplifier, and here you could have output impedances as well. Well, this one, but the load, if you have a load or like you have over here, that can be absorbed into what you would call the A circuit. So that becomes the A circuit. Okay? Then here, is your beta network and your sampling voltage. So you present the voltage as two ports with a reference over here and the actual voltage. And since you are outputting a voltage, essentially this becomes a voltage control voltage source with a gain of beta. So this voltage output over here becomes beta times this voltage over here, VO. And this can be applied to an actual simple negative gain op-amp type of amplifier with the two resistors giving you the gain or the beta. So in terms of calculating the input impedances, you can see here. So the output impedance would be, if this is a feedback network, you will see an impedance into it, as well as on this side you would also see an impedance into it as well. So you can also analyze the feedback network itself by putting an input, which is really what you're sampling, your output, and you will see that you get this feedback voltage out with an associated current. But the beta then becomes that voltage, and that's the last thing that I wrote on the pad. The beta becomes that voltage, VF, divided by VO, when the current is zero. When that current is zero. And what that says is that your feedback network does not load your input. So the fact that this current, we're making this current I10, says that this over here does not load, or the mixing does not load your input to the system. So those are some practical issues of these feedback configurations. But that was specifically the voltage feedback amplifier with series mixing, series voltage mixing, and shunt voltage sampling. Associated with the table that we went through in the pad, there are also let's see. There are also, oops. The other types. So here you have the voltage sensing. Regardless, that's just the sensing part. So this shows that you can have voltage sensing in or shunt sensing in parallel, or you can have current sensing in series over here. So you can see that. Okay. And then the next picture shows the two methods of coupling. So you can have voltage or series mixing, or you can have shunt or current mixing. So those two pictures give you all the types of sensing, and also something that is nice. So these two pictures are very important to kind of comprehend the overall strategy of how you do sensing and mixing for feedback topologies. Is also giving you the impedances, the output impedance here, on this side for the overall system, and here is giving you the input impedances for both types of mixing on the input side of the system. Okay, so these pictures are important. And there are other stuff and extensions that you can read. And again, the idea is that you read the book. So I'm going to leave this as something that you'll read 11.5.2 through 11.5.4. and also 11.6. So I'm going to just leave that for your reading, and we're going to go on to the next topic, which is important. That's another thing that we have to worry about when we have feedback, because as we discuss, we can have a situation that where feedback, which is supposed to do something good, it actually makes our system unstable. So we have to understand that effect or that side effect and how to guard against it. So we're going to talk about stability. Okay. To do that now, we're going to take a even more general approach and say that our closed loop gain, which we already stipulated that was dependent on frequency. But now we're going to say that our beta network also depends on frequency. So now it's a function of S. Okay? And then if we take a more direct frequency view of it, we can write the expression in terms of j omega. So that gives us a complex quantity for the closed loop response of the system. Okay, it's all the same. We're just expressing it as a complex quantity, but we still have the all important loop bandwidth. So in this case, that would be the A times the beta, which would be the magnitude of A j omega So what this is saying that there's going to be, since this is a complex quantity, it's going to have, in polar coordinates, it's going to have a magnitude and it's going to have an angle. And that angle is also going to be a function of frequency. Okay? So when is it that instability happens? How can I express that? So instability, what we want to avoid. Is when that feedback signal, which would be the loop gain at an angle of 180 degrees. So what is that omega at which the phase, which remember that the phase is also a function of frequency, at which the phase becomes 180 degrees, and in terms, my feedback is not negative anymore, because remember that my feedback is defined as negative in the mixing side. So if I always have to have a negative quantity coming out of the beta network. So, but I'm sorry, I always have to have a positive quantity coming out of the beta network, but if the angle now is 180, now I have reversed the sign coming out of the beta network. So the frequency at which that happens, I'm going to call omega 180. And here, same thing, because it's the frequency of the system and the phase of the system. And when that happens, if I get that sign reversal, I get an unstable system. Okay? At that specific frequency, essentially, the system will oscillate. It will be unstable, but it will be marginally stable in the sense that it will oscillate, but it will not be unbounded. In essence, the system, and this can be useful for some applications, you do want, oscillators are useful. That specific condition you may want to sustain and control, and that can be a useful circuit. But if you go beyond that point to where the circuit becomes unbound and what you are coupling is actually feeding with the input to produce a higher output, and that becomes, that loop keeps feeding itself to produce higher and higher outputs, then your output becomes unbounded until when? Well, practically until you saturate non-linearly and you don't have any type of output, of useful output from a linearity perspective. Okay? So we can also, for that point in which we have sustained oscillations, we can write a transient response.
Dr. Hernandez, where did the error input come from?
Hold on, I have to deal with my cat now. Sorry about that. Hold on. Tell me again your question, and I apologize for she's hungry, but she'll have to wait. All right. So what was the question?
In the equation above with x of I, where did the error input come from?
The error input?
Yeah, with x of f equals a jw180 times b jw180 times x of I. It's under instability.
So the x of f is the output of the beta network.
Yeah, and then x of I.
That is the input. That is the error. The error.
Yeah, I was wondering, like, is that just because of like the diagram we always see? Or?
Exactly. Yeah. So those nodes are that is standardized with those labels.
Okay, that makes sense.
Yeah. That's just saying that now the error reverses polarity. And now is feeding with the wrong sign into your basic amplifier, therefore producing a higher and higher output towards saturation or nonlinear behavior. Did that answer the question?
Yes, it did.
But at the point, so the important thing that I'm trying to show here is that at the point of omega 180, just at that point, because remember that the phase is frequency dependent. So it's going to vary over the spectrum. But there is going to be a specific frequency at which this happens. And that's what we call omega 180. And we can write a transient response for that specific point or condition. And let's say we're talking about voltage. That would be and that omega 180 will have a natural frequency. And that is the that is the expression. But the nice thing, and what I wanted to show here, and I don't want to erase it, so I'm just going to see if I can erase over here, so I can just write one last piece without having to okay. So the important thing is that this VT, okay, with this expression at that omega 180 is really it's really a sinusoid. Okay. Now we'll go back to, again, I'll do the same thing, kind of queue up the pictures and go over it towards the end. Now that as we discuss more on stability, and we want to reach back to what we just discussed earlier on today, where we said that this amplifier with a single pole response was a common case. We want to take a look at that in the context of instability. So let's do that. So amplifier with a single pole response. So this is common case. Okay? So we're just gonna go back to what we said before. This is your mid A sub 0, that's your mid-band gain. And we said that it had this response. And omega sub p is that pole. And we had said that the closed loop response for that was the mid-band gain divided by the amount of feedback so this is just another way of writing that closed loop expression. The only thing that we're doing now, just to kind of get our hands, get a handle on things one at a time, is that we are restricting beta not to be a function of frequency in this case. So beta is a constant in this case. Okay? And if we do that, we can see from the previous expression that the gain, so the gain is and for the closed loop case, the gain of the closed loop response is this expression, and the pole for the closed loop case So this is just a restatement of what we discussed when we're looking at the bandwidth extension. Okay. So let's look up. Let's look for the case where omega is much higher than the closed loop pole. So, and when I say omega, it's really interchangeable with frequencies. Remember, omega is just 2 pi f. So, the case where omega is much larger than the closed loop pole frequency. That's the case. Then in that case, if you look at the expression that I had in the previous board before I erased it, okay, what you'll find is that that closed loop gain simplifies to sort of, it approximates okay, and that's that approximates also the open loop gain. So that, in essence, this realization, very close approximation of what happens for at these higher frequencies, is really what gives us the property of the gain bandwidth product. Okay, and I'll have a picture to explain that more fully again when I go back to the pictures in a couple of minutes here. Okay, I think that yeah, perhaps it's a good time to go back to the book and look at these pictures before we get too ahead of ourselves. Okay, usually in this course I make a lot of use of the two-screen setup that we have in some of the classrooms, where I can in one screen I show the book for the pictures, and in the other one the board on the other side next to it, the board I use for writing. But haven't figured that out, how do you do that in Zoom. So this is, I think, the closest I can come up. I can come to that. So let me go back and switch to the book and look at these pictures. This is the effect of the poles on the amplifier behavior. So when that feedback is negative, meaning that your pole is on the left-hand side of the plane, your transient behavior will be such that the oscillatory transient behavior will die out, that component. So you will, your amplifier will settle to some specific output for some specific input. That's what this refers to. And then if you have um, your poles in the right hand side of the plane, then you have the unbounded behavior, because at that point your feedback is being made greater than 1 overall, because it's negative, but not at the omega 180. So the amplifier and the system is feeding into itself, so you get this unbounded behavior until it saturates. And this is where you have the case where the poles are right at omega 180. So you got the oscillatory behavior. And we'll see later when we study oscillators how we actually can make nonlinear circuits where actually your poles start a little bit on the right side, so you can get starting, you can start the oscillation going, but then you don't want that to be sustained forever. You want the poles to actually so we're going to study how to make oscillators. You build these nonlinear circuits that the pole is slightly on the right hand side, so you slowly build the oscillation, but then when the oscillation has built to the point that that you're happy with, these poles essentially travel and they get parked right here on the axis. So now you get the sustained oscillation. Okay, so that's how oscillators are built. The poles actually in the circuit move dynamically as the oscillation gets larger. So pretty cool. So we'll have a whole chapter on oscillators and we'll discuss that. But the fundamentals of it is right here. We're discussing that right here, right now. Okay. So let's see. So let me erase these things here. And let's look at another few figures. All right, and we saw this a little bit. The principle of the gain bandwidth product. Okay, so basically, but this figure adds the dimension of the S-plane. So we had already seen this and the effect of the gain bandwidth product earlier on today, but then this is a representation of that in the S-plane. So essentially, this is the pole, the open loop pole. Here we are extending the bandwidth, right? Making that pole more on the negative side. So this would be the closed loop pole here. And this is the open loop pole here, okay? So in the S-plane, that's how it looks. In the gain versus frequency or a spectrum plot, or in this case it's a body plot because this is with the straight lines, that's how it looks, okay? All right, so let's see. I am not covering 11 8 4 and 5 because as you can imagine there's no reason not to have amplifiers with 2 poles, but we're just saying that we only have one. And yes, realistic amplifiers can have more than 1 pole, but what we say in that case is that we have 1 dominant pole, and then we can use techniques of frequency compensation to diminish the impact of one pole. So if we have more than one, so that we still have 1 dominant one, and we can treat everything as a single pole amplifier, which is very straightforward. If you have 2 poles, then you have to employ other techniques that you have seen, like root locus and things like that. But I'm not covering that because this is not a control course. It is a circuits course, and we want to be practical in that sense, and we have a lot to cover. So we're not going to be covering 11.8.4 and 5. What I do want to show are some other pictures, and want to show 2 other pictures. 11:37. So here, so these pictures shows the concept of phase and gain margins. So if you graph the gain, so the gain here, and the phase of the open loop system, okay? So this is the open loop gain. I'm sorry, not the loop gain, not the open loop gain, but the loop gain, which is A times beta. If you look at the frequency response of that network and you graph the gain and the phase, here you can see the omega 180. That is the frequency at which the phase is 180. Okay? Now, at that frequency, you want the gain to be negative, going this way, because now you're going to have more of a negative phase. So how far at that frequency you are, okay, from your gain to becoming negative, that's called your gain margin. And you want this space to be as large as possible, okay? You want this to be as large as possible, which implies that you want your response to decay faster so that, you know, this is larger, okay? That is your gain margin. On the other side, the frequency at which your gain is 0, so you are at that point to cross the threshold from positive loop gain to negative loop gain, which is a bad thing, when you are past the 180 phase. So how far you are from 180, that becomes your phase margin. And you know, normally you want like 20 dB of phase margin and 45 degrees of phase margin. So 20 dB of gain margin, 45 degrees of phase margin, that's adequate. You don't want to be too close. What that says is that, again, you want your response to either decay faster, or you want your phase to extend into the higher frequency, which is extending the bandwidth. So extending the bandwidth makes your system more stable, but making your phase margin greater. Because now, if you look at this, now the phase margin would be something like this. So feedback, for the purpose of increasing the bandwidth, is a technique of frequency compensation. And at the end of the day, when you are working with circuits, all this is, you verify and design with SPICE. But you have to have an intrinsic sense of understanding for what you're doing. It's not like plugging things in SPICE and connecting things and doing simulations, because what you end up doing is wasting a lot of time, spinning your wheels, and not really making any progress, because your choices are not educated by understanding. So that's why it's important. I'm not implying that you're going to be doing any type of real circuit design by pencil and paper, but it is very important to have that understanding, so you make the right choices and are intentional about the designs that you do.